So I promised you we'd start with a challenging topic of some sort. And so the topic that we're going to look at first is called working with surds. Um, I'm going to only go for your level 3 and 4 questions here, with surds, because I know that the textbook will give you all the skills that you need for level 1 and 2 questions. Okay, so there's a couple of things that I want us to remember. First of all, you need to know your surd laws really well. Okay, so you need to know that when you multiply two like surds, by that I mean both square roots, both cube roots, you are allowed to multiply what's under the roots. So you've got the square root of a times the square root of b, which you can now say is the square root of ab. When you're adding surds, it's even stricter. It's like algebra. So you basically can only add or subtract like surds, meaning that they must both be root A or they must both be root B before you can add. So 2 root A plus 3 root A gives you 5 root A. Right, then you also need to know your exponential laws and rules. So I'm not going to go through them now because your teachers have done that. But as we use them, I will remind you of the 4 laws and the 2 rules. Your notation for surds, remember that what's in the exponent remains in the numerator of your rational exponent, and what's outside the root, your square root, cube root, fourth root, etc., that becomes the denominator of your rational exponent. Okay, then I just want to recap rationalizing the denominator. I do have reason for this, so there's method in my madness, and you'll see when we come against some of the more challenging questions. So the reason we rationalize the denominator is because in maths, we're not considered to be giving an answer in simplest form while we have a surd in a denominator. Okay, so if it's a single fraction with a surd in the denominator, it's super easy. You're just going to multiply numerator and denominator by the same surd. So think about it. If I multiply by root 2 over root 2, would you agree I'm actually just multiplying by 1? So I'm not changing the 3 over root 2, but now there's no rule that says I have to go and cancel the root 2 over root 2. So what I'm going to do instead is I'm going to multiply numerators together, and I'm going to multiply denominators together. And what I've done is I have turned it into a fraction with a rational denominator. If you go and type on your calculator 3 over root 2, your calculator will automatically tell you it's 3 root 2 over 2. So your next question is, well, why can't I just use a calculator? Sometimes the question is going to require you to have that understanding in order to answer the question. The calculator won't give you the understanding. Sometimes it says without using a calculator, and then you've got to show the step of working. Right, the second one is a little bit more complicated because now we have a complex denominator with a surd. So now you're going to do an extra clever thing. You're going to multiply. It's got a fancy name, but I'm not going to go into fancy names because nobody's going to examine you on the fancy name. Can you see that I've got exactly the same binomial, except instead of a plus, I've put a minus? And there really is method in my madness here, because when you multiply these two together, you've got the equivalent of a difference of perfect squares in the denominator, and that's your aim. So in the numerator, I've got to multiply that 3 by everything in the numerator. So I'm going to have 3 root 2, and then I'm going to have minus 3 times 3 is 9. So that doesn't look very simple, but in the denominator, root 2 times root 2 is 2. My outers minus 3 root 2 and my inners plus 3 root 2 cancel with each other. They subtract to make 0 because it's a difference of 2 squares, and I've got positive root 3 times negative root 3, which is minus 9. Okay, now don't get all excited and think you can cancel the minus 9s. Of course you can't, because that is one term and that is one term. Okay, because of the division line. So at the top, I have 3 root 2 minus 9. At the bottom, I've got minus 7. Okay, I've deliberately chosen an ugly one here. Sometimes you're lucky and they actually do simplify further. This one isn't going to simplify further. So if your teacher's really fussy, they might say to you they don't want the negative at the bottom. So you can either put the negative here on the side, or you can say let's divide through by a negative and make it 9 minus 3 root 2 over 7. All right. I'm not so worried about the answer. I'm worried about the process, that you understand how to rationalize the denominator when you have something that's a little bit complex like that. Right. So those are just your basic skills. Now let's go and look at some actual questions. All right. This first question is a good old favorite. It pops up from time to time. It doesn't have to look exactly like this. But what I can tell you is you must look out for the going on to infinity, right? If it doesn't have that, then you're doing a different question with a different technique. So this is that you continue in the same pattern until infinity. All right. So here one can get a little bit stuck on the approach, because the one approach is that you change all of these square roots and you rather make it 12 to the half or bracket to the half. The pluses make that a little bit messy here. The other approach is when you have a square root on one side of an equation, you square both sides to get rid of the square root. And over here, you look at that and go, well, what's the point? I'm only going to be able to get rid of one square root. Okay, so I'm going to show you what is the point. And the point, the reason that we're going to take that approach is because of the plus dot, dot, dot. Okay, so we're going to square both sides. So we're going to go x squared. And we're going to take this whole horrible, ugly, big surd. And we're going to square it as well. Okay, by now your arm's already tired just writing all of this. Okay, but you get the idea. Okay. All right. So when we square both sides, on the left, this becomes x squared. On the right, the only thing that we get rid of is this first, the biggest square root sign. So we're now left with 12 plus, and then the rest just carries on. And at this point, you're feeling just a little bit like, oh, why did I bother? Because it looks like we haven't made any progress. Okay, the good news is we actually have made progress. First of all, I can take the 12 and subtract it on both sides. The other good news is what I'm left with. You can definitely get tired of doing these square roots over and over again. Would you agree that what I'm left with here, in essence, is no different to what I had right at the beginning? Okay, look really closely at that and that. Don't tell me no, but there's 4 root 12 pluses over here and only 3 here. Because remember, the dot, 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 the to infinity is telling you that they go to infinity anyway. So it doesn't matter whether I write down 4 or 5 or 10 or 3. So this is the same as this. But if they're the same, then why can't I just replace this whole bracket with x? So I'm left with x squared minus 12 equals x. And at that point, you can sigh a huge sigh of relief because you've turned it into a simple quadratic equation. I'm assuming that you can factorize a quadratic. And so x is equal to 4 or x is equal to -3. Now, because we squared both sides and turned it into a quadratic, we've actually got to check our answers. If we check this one, can you see that it tells us that x is a negative number? But if you go back up here, if this is a negative number, you're saying square root of all positive numbers adds up to a negative, which is impossible. So this solution is not applicable. Okay, it's better to say not applicable than x is not equal to -3, because x is equal to -3 for this equation, but the solution doesn't apply to the original equation. So the final answer is x equals 4. And the strange thing is, if you were to go and sit with your calculator and put a big square root and go 12 plus, square root 12 plus, square root 12 plus, and you do that about 5 or 6 times, you will see that your answer comes out to be 3,99999 something, which is pretty much x is equal to 4. Okay, so if you don't believe me, you can go and check it out. Right. The second question is much more mundane. So let's have a look at it. Solve for x. The only hassle here is that you have a square root on both sides. So we're going to use the same technique that we used for question 1, because I know that I've got to get rid of the square roots. But when I square both sides, I have to be careful and remind myself that I'm squaring the whole left-hand side as one perfect square and the whole right-hand side as one perfect square. So when I square the left, it's going to be 2 squared, which is 4, and I'm squaring the square root, so it falls away. On the right, I'm squaring a square root, so I'm left with -36x. If it worries you as to why, when you square a square root, it falls away, just remember square root is actually a power of a half, and a half times 2 is 1. Okay, now it becomes a very, very ordinary quadratic equation. So we've got 8, it's not even quadratic, 8 minus 28x minus 36x. But bring the 36 to the left, I'm going to go minus 28 plus 36 is 8x. So x is -1. If it worries you, you can go back and check to see whether it actually works. -1 minus times a minus is a plus, so it's root 36, and root 36 is 6. On the left, -7 times -1 is 7, so it's 2 plus 7 is 9. Square root of 9 is 3. 2 times 3 is 6. So the answer is correct, and so I know I'm done. Right, let's try 2 more, and then we're going to end this video. I'll make a second video with the next lot of questions. Right, this was in the November 2018 DBE final exam. It's quite a nasty question. So the first thing I thought of was oh, but look, these are both equal to 64. So I wondered whether it wouldn't be a good idea to make 3 to the 9x equal to 5 to the root p. But when I stopped and thought about why would I do that, I thought I'm doing that because I'm trying to solve for x or to solve for p, and I'm going to have different bases, different exponents, and I'm going to be stuck. So then I thought, okay, that's not what the question says. The question says if that and that, calculate without the use of a calculator the value of. So they don't want me to get rid of the 64s. They want me to come up with actual numerical values for this numerator and this denominator. And the moment that I actually processed the question and thought, what do they want? Then I realized I don't have to put these two together. I can work with them one at a time. So first up, I thought I'm going to work with the 3 to the 9x. And I'm going to see if I can get it similar to the numerator. So would you agree that my numerator is the same as that? Okay, I'm using an exponential law that says a power to a power means you multiply the exponents. Okay, so with that in mind, I'm going to say 3 to the 9x equals 64, which means 3 to the 9x is 2 to the 6. Now, I can raise both sides to the 1/3. And you're going, how did you know to do that? And I'm saying because 1/3 of 9x is 3x, and that's what they're after. This is a level 4 question, by the way. So 3 to the 3x is equal to 2 to the 2, which is 4. But I'm not done. I want it to be 3 to the 3x minus 3. So 3 to the minus 3. What's 3 to the minus 3? Think about it. Yes. 3 to the minus 3 is 1 over 27. It's 3 cubed, which is 27. So it's 1 over 27. So what about if I take the leap and I say, let's put these both over 27. It's allowed. It's an equation, so whatever you do to the left, you do to the right. And now I can say this is 3 to the 3x times 3 to the negative 3. I've brought that 27 to the top. Equals 4 over 27. One last step, 3 to the 3x minus 3 is 4 over 27. So I have now dealt with the numerator. I have an answer. Okay, now we're going to look at the denominator. The denominator is much closer. The only difference is I've got this sneaky square root over the 5. So for a moment, I want you to think, what does square root of 5 mean? How else can I write it? Oh yes, I can write it as 5 to the half. Okay, so I'm going to use that trick. So I'm going to go to what was given, 5 to the root p, and 64 is 2 to the 6. And I'm going to say, let's take both sides to the half. Can you see I'm using exactly the same technique twice over here? So on the left, I've got 2 to the 3, 2 cubed. Sorry, on the right. On the left, these are multiplying together, but there's no rule that says that the order has to look like this for multiplying. So multiplication is commutative. So I'm going to say, I can also write it like that. And that is the same as root 5 to the root p is equal to 8. So what have I got? I've got that my denominator is equal to 8. So therefore, the whole expression is the same as 4 over 27 divided by 8, They do say without a calculator, so I'm going to be very good and not use my calculator. And I'm going to say it's 4 over 27 times 1 over 8. And when you're done with that, it's 1 over 54. All right, so that was a full-on challenge of a question. What did I use? Actually, exponential laws and the fact that I can raise both sides to any power that I want to, as long as whatever I do to the left, I do to the right. Okay, so really, really good question, November 2018. Don't let anybody tell you that there weren't difficult questions back in 2018. Okay, last one for this video, and then you can wait for the next exciting episode of the next video. This one, so I'm just going to move my page. This one says, this was November 2020, those poor matrics of 2020. If n is the largest integer for which n to the 200 is less than 5 to the 300, determine the value of n. All right, so 2 important words here, largest. So we're not worried about a minimum value. And the second important thing we're thinking about is it's got to be an integer. So no fractions, no, it's got to be a whole number of some sort, positive or negative whole number, but it's got to be an integer, no decimals. So chances are I won't use logs. Chances are I'll be able to solve it without logs. Okay, now for the tricks that the examiner has put in here. Bases are different, exponents are different. So I can't use any of my normal techniques for solving an exponential equation. I want to try and force it to get into one of those techniques. So I look a little bit more closely at the exponents. And when I look at the exponents, I notice that they're multiples of 100. And I go, what if I use that? How do I know that? Well, I don't know what else to do. So I'm taking the only thing that they have in common. So n to the 2 to the 100. You see, I'm using that same law, a power to a power you multiply, equals 5 cubed to the 100. Okay, so now both are to the 100. So technically, I'm allowed to do the 100th root on both sides. And what am I left with? N squared less than 5 cubed. That was careless of me. That's a less than sign. So what is that? N squared is less than 125. The correct approach here is to do a quadratic inequality. So what you would do is you would turn this into a difference of perfect squares. And then you would get your critical values, which would be the square root of 125, which should be 5 root 5. And so I would say my solutions are between minus 5 root 5 and plus 5 root 5. It's a less than 0, so it's this part of the parabola. Okay, so minus 5 root 5 less than n less than 5 root 5. Now keep in mind that we are only interested in the largest integer. So what we know here is that n is less than 11 comma something. And we're not interested in the comma something. So we can say with absolute conviction that the largest integer that n can be is actually 11. And once you've got that sorted out, then there's nothing more to worry about. We know that the largest integer in this case is indeed where n is equal to 11.